In progress.
Okay. So the idea is like students give test. Okay, students give test. Suppose in one subject you gave test one. Okay, what happens in test one? You don't really know what are the questions, how the teacher asks the questions and all. So therefore, many chances are like you might have practiced only numerical problems, but theoretical questions also come, and you might miss. You might miss. Due to that, what happens? Your mark will reduce. Okay. When you conduct the second test, what's the chances that you already now know that there are both theoretical questions going to be asked as well as like numerical problems. So you learn both of them. You learn from test one. Okay, you learn from test one data and then you apply it to your test two event. Okay, and that way test one it has decreased, so you know how questions are being asked, and then test two you are prepared. You apply the question, somehow your mark will definitely be improved. Okay. So motivated, we want to study the relationship between these two tests. What happens between these two tests? Okay. So that is this question. So you want to see how students' performance has increased over the year, over the test. Okay, that is not some reaction test. So student, yeah, first test X. This is the second test Y. Okay, I need 8 names. Volunteers. Platform. Okay. Then anyone else? Correct. Anyone? Okay. Tell, huh? What's his name? Okay. So these are the marks. Like it might be other way around also. Like those who performed well in first test might get overconfident and score less in the second test. Okay. So therefore, you don't see the what you call the progression always. There are ups and downs. Okay. So keep in mind that the number don't really reflect. Okay. So you have to compute the regression line between them. Okay. So that's the idea. So I think you already know how to do this because given two data sets, how you can compute the coefficients of the regression, that is the intercept and the slope. Okay. So using this data, your job is to compute it. So please. So compute the equation of regression line. Compute the regression line. That's the idea. So to see how students' reaction skills have improved over a year, 8 students took this test at the start of the year and at the end of the year, and these are the scores. Okay, so the first test in the start of the year, second test towards the end of the year. So to see whether the students have a, so try. You don't need to know. All both are in the same mark. 100. Yeah. So start doing it because yeah. What you need to compute? What you need to compute? What all things you need? Sigma x, sigma y, then sigma xy, then sigma y square. Using these, you have to compute the y cap equals to a plus bx. Yes. How to compute a and b? You already know. You already have. Yeah. So we got a to b minus 8. Okay. B is okay. So this is the line that is y bar equals to a plus bx. Sorry, y cap equals to a plus bx. Okay. I suggest try to plot these points in Python and draw this line and try to see whether it is actually kind of fitting or it is not. Okay. Fine. So through this you can actually predict here, if given any other data here, x, you can actually put this value here and predict what can be the plausible case. Okay. It might not be the same, but you will get somehow nearby that approximately. Okay. Similar questions can come like with an applied example, okay, in your exam. Like it can be given that weight of one quantity decreases over time. Okay. Can you give me an example where weight decreases over time? Hmm? Where weight decreases over time. Ice, but water weight will be the same, right? Camphor, 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 like sublimes, the sublimation process. Camphor sublimes. So therefore, weight of camphor will decrease over time. Okay. So what scientists will do to understand how the sublimation happens, they will record. Okay. This is not the duty of a chemical engineer. This is not the duty of a chemical engineer to monitor how much it happens. It is the duty of a statistician. Okay. The duty of a statistician. Okay. So what the statistician will do? He will monitor the weights. He will monitor the weight. Like t equal to 5 seconds, this is the weight. T equal to 30 seconds, this is the weight. T equal to 5 minutes, this is the weight, and so on. And using those weights, you can do a least square. Okay, because you can do a least square because you have all the data available with you. Yes. So you have to predict after 30 minutes. So you want to know, the camphor company wants to know whether how after how much time the camphor is gone, like the weight is 0. Because then only they can understand how much this camphor can help a person. Okay, because you use the camphor and if it lasts only for 5 minutes, not good. At least it should work throughout the day or throughout the like the time period you are having work with that camphor. So you need the time. So therefore you need to predict the time after which the camphor gets like 0 weight, okay, or fully sublimed. Okay. To do that, you need to use regression. So that kind of question might come given the data set, but the question flavor is a bit different. But the idea is the same as this question. So fine. So what we have been doing so far, like is given the set of data, you find the linear line. Okay, y cap equals to a plus bx or w naught plus w1x. You know how to compute w naught. You know how to compute the coefficient w1. Yes. Now let us come into a different kind of problem. Okay, for nonlinear function, least square regression for nonlinear functions. Okay, suppose you have a nonlinear function and you know your data is kind of behaving nonlinearly. Then how to attack that problem? The concept is similar. Concept is similar. You can boil. So it's not. I'm saying not saying this for a generalized problem. I'm saying this for some special cases. You can sometimes boil down the nonlinear function to linear regression line. Okay, of the form y cap equals to a plus bx. Okay, so how to do that? How to do that? Okay. Suppose you have a function. Assume this is assumption. Assume you have a function of the form that is y cap x is this alpha e to the power beta x. Okay, for some x and y. For some x and y. Okay. The idea is like how you can find this alpha and beta. You know, suppose you have a data set. Suppose you have a data set which increases like this. So you know your data set is exponentially increasing. Your y value is exponentially increasing as x value is increasing. Yes? Can you understand this? Y value is exponentially increasing as x is increasing. So in order to model this, what you will use? Will you use a linear line? If you use a linear line, it is not a good choice. Okay, so you need to use something which looks similar to this. Okay, it should be a curve. So the first step comes to your mind is like, yeah, it is increasing exponentially. Like it is increasing not linearly, it is not increasing not in a proper way, it is like increasing in a very fast way. If it is increasing in a very fast way, what's the first thing should come to your mind? Exponential. Okay, anything increasing at a fast rate, you always give the word exponential to. So therefore, you will tell y cap equals to some alpha e to the power beta x. You already know your data will follow some kind of this function pattern. Okay, that's the idea you have. Now, what's the next step? Your next step is to compute what is the value of alpha, what is the value of beta. Can you compute it? That's my question. Can you compute? That's the trick. That's the exact trick. But you have solved 50% of the problem by saying that this data set can be approximated by an exponential function. Okay. So after this, our job is to compute how to find alpha and beta. How to find alpha and beta. Okay. So how to find alpha and beta in this? Any ideas? Any ideas? I'll give you some time to think. How can you proceed? Any ideas? Hmm? Yes, you can use logarithm. And that intuitively comes to mind because wherever you see some multiplication, wherever you see some exponential, what can be done to simplify those things? Apply the log. Okay, apply the log. So if you apply log to both of side of this equation, what you get? Log y hat x equals to log alpha plus beta x. Can you now see that this problem is somewhat familiar? Is this familiar to you? Is this problem familiar to you? You can write this as capital Y hat equals to W naught plus W1 of x. So you can see how this nonlinear function approximation can be boiled down to the least square problem. Can be boiled down to the least square problem. Okay. So you can compute this alpha and beta here. Now still 90% of the job is done. 100% is not yet done. What is the remaining 10%? What is the remaining 10%? So you know W naught is log alpha and you know W1 is beta. So you don't have to do anything for W1 because it's already equal to beta. But you also need to know alpha. You also need to know alpha. How you can compute alpha from here? Alpha equal to exponential. Yes, that's the simplest form instead of log inverse. Okay. So alpha equal to e to the power W naught and W, sorry, and beta equals to W1. So you can easily find alpha and beta now, and it can easily approximate your data. Okay. So with this alpha and beta, you can actually find y equal to y hat equal to alpha e to the power beta x. Okay. So can you see that the problem has been solved just by using an idea that you can apply the log function? Okay. Is it okay? So we will take this example with alpha equal to 0.1, beta equal to 0.3 in Python. Okay. Maybe I'll show you now. Hmm. Okay. Yeah. So see this log trick here. Okay. So we are generating the data set here. So, sometimes it's not the case. But whatever machine learning project you work on, if it is totally new, if it is totally new project you will be working on or you are interested in working on, you have to always generate your data set. Generating and machine learning can only work with huge amount of data set, not in small part. Okay, huge amount of data set. Okay, why Google is working so efficiently? Why ChatGPT is working so efficiently? Because it has lot of data stored in it. It has trained over a lot of data. So whatever you ask, that is being already trained on. It is already being trained on that data. And when you ask that question, it gives you an answer based on the data he has understood. Okay, just remind me in this question when I come back to slide. I will tell you one more thing. Okay, for now, let us generate our data set. Let us generate our data set. So can you see your data set x equals to np.lin space 0 to 10? You are dividing your x set of data into 100 points from 0 to 10. Okay. Y equals to exponential set of data 0.1 exponential 0.3x. I am just artificially producing this data. Okay, I am artificially producing this data. Understood? Artificially producing this data. Yeah. And so that it doesn't only appear. See, if you just consider this alpha e to the power beta x, it will just come to you like this, purely exponential. But you don't want to look like this. You want to have some noise in it. So therefore, we are adding that noise down. 0.1 np dot random length of x. Okay. So whatever for each value of x, there is some randomness associated to it. So therefore, if this is the true point, that is alpha e to the power beta x, if you add the randomness, this point might be here or here in a particular buffer. It will be in a particular buffer randomly, like randomly it will be distributed. Okay, that's what you will see in the plot. So this is our data set, and our job is to find the regression to this data set, regression curve to this data set. Okay, so I plotted this data set here. So this is how it looks. Can you see that it is behaving like the curve alpha e to the power beta x, but it is actually not a curve. It is actually not a curve. Okay, why it is not a curve? That there are some ups and downs because of the randomness I have added. Okay, so therefore you can see that this is the curve, but it has noise associated to it. Okay, fine. Our job is to find which regression curve fits this data. Which regression curve fits this data? You already know the answer. You already know the answer because this data set is actually 0.1 e to the power 0.3x alpha e to the power beta x. So therefore, if you do the regression line properly, it should kind of give you the similar values. Okay, that's the idea. That's it. That's a method to double check whether your method is working correctly or not. Fine. So this is what we are doing here. All the ideas that what we have seen in the slide is applied here. Okay. So what we are doing, log alpha. That yeah, why I'm not understanding these terms. You just need to know that this idea is applied here. Okay. So you can see LSTSQ, that is the least square function is applied here from Python. It only needs that matrix A and the Y. Okay. So both you give, it will give you the coefficients. Finish. Okay. You don't have to do anything more. Okay. So you can see alpha is coming to be 0.14, beta is 0.26. What is the actual value it should have come? 0.1 and 0.3. You can see that it is coming somewhat closer to those values. Instead of 0.3, it is coming 0.26. Why it is coming like that? Because of the added randomness. It is not the actual value. Because of the added randomness, it is kind of coming or deviating from that set. And we plot this y cap equals to alpha e to the power beta x. Okay. Is the output. Okay. So you can see that somehow, mostly you can see that our regression curve follows or approximates the data set. Okay. So you got an idea. Even for nonlinear functions, of course, you cannot directly apply to sine function or something like this. Log function, exponential function, like this, or squared function, you can apply these tricks where the problem finally boils down to the least square regression. So therefore, how much advanced regression techniques you learn, it's fine. But you always need to know least square regression. You can see how complicated nonlinear problems can be boiled down to least square regression. Okay. 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 So that is the exponential data. Okay. What other data sets can you apply this to? Any ideas? Suppose y cap x is some b x to the power m. Power functions. Power functions. You already know that some of the most of the real world problems or any real world quantities you deal with, chemical engineering processes, or anywhere scientific industry, your products will vary with the power law. Your products will vary with the power law. Okay, power law means it will vary like this function y cap equals to b x to the power m. Okay, so our job is to find what are b and m. Okay, you already know that suppose your function looks your data set. So what you do, you gather the data. What's our idea? What is our take? First, obtain the data set from the company. Okay, obtain the data set from the company, plot the data set. Okay, you will plot the data set. How it looks like? Suppose it looks like this. Okay, then what should be your step? Yeah, how I can understand, how I can predict that after this x, what happens? Up to this x, you know what happens at this x. You can only predict using regression. Okay, so how you will use the regression concept? Data set and feel that yes, it is kind of exponential data. Okay, it is kind of exponential data. So I should use alpha e to the power beta x to fit it. Okay, or it is not behaving that fast. It is not changing that rapidly. So therefore, if it is changing, not changing linearly and also not changing rapidly, that means it is somewhere in the middle. And somewhere in the middle means you can use power functions. Okay, power functions grow less rapidly than the exponential. X square e to the power x. X square will be a bit slower than e to the power x. Okay, you can plot and see. So y cap equals to b x to the power m. How you can compute b and m? It's the same idea. Apply log again. Apply log again. So log y cap equals to log b plus m log x. Fine. Is it okay? So can you see that this is now y cap, this is w naught plus w1 capital X. Okay. So therefore, your nonlinear functions can always be boiled down to linear case. Okay. So you can do that. Same you can do with polynomial regression. Polynomial regression. Can you apply some tricks to polynomial regression? What do you think? Suppose y cap. Suppose you have the function. Suppose you have the function f of x is this a n x to the power n. Like it behaves in a polynomial fashion. It behaves in a polynomial fashion so on till a1x plus a naught. Your job is to compute all these coefficients a naught to an. Okay. How can you compute? Job is to compute AIs. How you can compute? Any ideas? You need to compute AIs. How can you compute AIs? See, you cannot apply now log form. Why you cannot apply log form? Because addition is there. Addition terms are there. There are addition cannot help you in terms of log. When multiplication is there, log is very much helpful. But when addition is there, log won't come helpful to you. How can you do it? Can you think? So if your function behaves like a power function, but you can see that recall your last classes of computational science where we added different sine cos terms to create the Fourier transform and all this. Normal equations. You can solve using normal equations. Yes. But we will see, since I have covered that in the computational science class, I will tell you that in Python you can solve this. Okay. There is something known as polyfit and polyval. Okay. Polyval, what it will do, it will evaluate that polynomial at different points at different values. What is polyfit? If you give the set of data x and y and the order of the polynomial you want to fit, you will tell, I want to fit a third order polynomial to this data set. I want to fit seventh order polynomial to this data set. So you plot the regression line and check which order of polynomial fits the data set properly or accurately. Okay, that example we will see in this class. Let us go to Python. Yeah. Okay. So this is the case I wanted to talk to you. So we can use this numpy.polyfit to obtain the coefficients, that is a0, a1 up till an. That was our question. Those are the coefficient of different order polynomials with the least square. With these coefficients, we can then use numpy.polyval. With this, after you obtain the coefficient using polyfit, you can evaluate, you will get the polynomial. But what is your job now? After getting the polynomial, to evaluate the polynomial at some unknown x, so as to predict the value of the polynomial. Yes. So if you want to use it, you don't have to write all the big polynomial equations. You can just polyval. You can just use polyval. Okay. To get specific values for given coefficients. Fine. So yeah. So you can see this is your data x. This is your data y. Okay. X set of data and y set of data. You can check that size of x and size of y are both the same. Size of xd and size of yd are both the same. My job is, given this data set, I first plot this data set x and y just to see how it looks. Then what I do, I know I have to use polynomial regression. I am confirmed in my mind. There is still 90% of job is done, but 10% is still there. What is that? I know I have to do polynomial regression, but there is one aspect I don't know. What is that? Yes, degree we don't know. Like I told you, we can use this polynomial regression for this data set. But what order of polynomial I want to fit? Second order, third order, fourth order, fifth order, what? I don't know. So you don't really know which degree you have to fit. So for that, I am doing a for loop for I in range 1 to 7. So I want to compute all the degree polynomials, second order, third order, fourth order, fifth order, sixth order, just to check which fits properly, and I will plot each of them. Okay, I will plot each of them. Like you can see, this is np.polyfit. xd and yd. These are your given data sets, xd and yd, comma I. That means I am giving the input that given these data set xd and yd, I want to fit ith degree polynomial, and I is 1. When the for loop happens, I will be 2. So at every loop, you are fitting a polynomial of order I into the given data set. Okay. So you can see finally what I am doing, plt.plot. Okay, plt.plot xd comma yd, and I'm plotting those data set, the raw data set using magenta dots. And then what I'm doing, plt.plot xd comma np.polyval, the y estimated, that is using polyfit the output, comma xt. Okay, it will evaluate the polynomial. See, you got the polynomial, but no one evaluated the polynomial for you. You have to evaluate that polynomial. Then only you will get the regression points. Okay, so you have to evaluate that polynomial. Fine, and that we are plotting in orange. So that is clear. Okay, your given data set is being plotted in magenta, and your polynomial regression curve is plotted in orange. Okay, for different order of polynomial degree. Let us see. So this is that output. Okay, this is the output for polynomial order 1. That is like a straight line, mean square. And this is the actual data set. You can see what this reminds you of, the actual data set. What this actual data set reminds you of. Yeah, it's kind of sine. Okay. So therefore, you can check that this data set is given from sine. Okay. So you can take this. Okay. So this is polynomial order 2, which behaves like a bit of a curve. Polynomial order 3, you can see it kind of approximates, kind of. When you take polynomial of order 4, yes, very, very close, still 2 points out of it. Polynomial order 5, this point got closer, this point is still out of it. Polynomial order 6, this point, the gap reduced much. Okay, so I will use polynomial order 6 because, yes, most of the points are already covered, and only 2 points are very close to each other. Okay, you can similarly do polynomial of order 7, polynomial of order 8. Okay, like that. Fine. I hope this is okay. Okay, finally, like whatever happens, whatever be the case, the idea is simple. If you don't want to use all these complicated formulas of SXY, SXX, sigma X, sigma Y manually, you can just use this optimized curve fit algorithm from SciPy. Okay, and give this data set A and B, AX equal to B if you want to do. Okay, and it will compute the coefficient W0 and W1 for you, or A plus BX, A and B for you. Okay, how many examples we saw? What other functions we saw? We saw LSTSQ. We saw LSTSQ, that is doing a least square regression line for you for the given data set. Okay. Now we are seeing curve fit. Okay. So let us see this. You suppose you don't want to do the log trick. You say like, I don't want to do this log expression. I did log in my class 6th or 7th. I don't want to remember it. Okay. So you do optimize.curve fit. Okay. Let us see. This is the function y equals to a and p dot axp bx. A e to the power bx. The same thing we did in the previous examples. Okay. So what we are doing, we want to find the coefficient alpha and beta. So just use optimize.curve fit. The function, that is func means this. It will give you the output y. That is a e to the power bx. Fine. And this is the x data equal to x. X you already give as input. X is like an array. Okay. And y data is y. This is coming from this func data. Okay. All the things you gave to optimize.curve fit. What you gave? You gave the x data set, you gave the y data set. And you say you find a regression line for me. That is it. Optimize.curve fit, comma this. And this. You see, this is the least square regression line it is giving. Alpha equal to 0.12, beta equal to 0.27. Okay. You can actually see that this value is actually bit efficient than your log, manual log computation. In log, you are getting 0.26. Now, using this curve fit, optimization.cofit algorithm, you got 0.27. So some improvement you have. Okay. Actual answer is 0.3, but still. So you plot it using optimized.cofit, you can see that almost similar as you did using the log trick. Is it clear? We did using two things. We did first using log trick. You are getting something similar as this. After this, what we did? We used optimized.cofit algorithm. And using that also, we got the similar curve. Okay. So that is, I think, fine. So this is all about the regression I wanted to cover. Now you know that how to use regression. How to use regression. What we learned in regression so far? Least square regression. Then we learned Python, LSTSQ from LIANG package. Third is, yes, least square using nonlinear functions. That you can use some log tricks. Okay, nonlinear means like you can use exponential. Then you can use power functions. Then we also learned about polynomial regression. Polynomial regression using like Python, that you cannot use the log trick anymore. So you have to use polyfit and polyval. Okay, those are the algorithms. Fifth is optimize.cofit. Like you don't have to use any analytical form. You just have to give XY data to this. Okay, and it will evaluate your regression curves. So you can see optimize.curve works with anything. Optimize.curve can work for both linear as well as nonlinear functions. Because we gave a nonlinear function to it, a to the power bx, and it still worked. It gave you what is alpha, what is beta. So therefore, optimize.curve also works properly. Fine. Okay. Most importantly, we did not cover this we covered in class. You don't remember. Generalized Penrose inverse, Murray-Penrose generalized inverse. Generalized inverse. And we also saw that is y cap equals to okay, beta equals to okay. So therefore you can see, and we also saw that Python has an inbuilt function pinv pseudo inverse to compute this. We saw why you need to use it. You need to use it when y is a function of multiple variables. Y is a function of x1, x2, x3, so on. Maybe in the next class we can consider one example of this case. Okay, fine. What else we are going to learn in this course, in this lecture, sorry. So we will see now how regression is connected to neural networks. Regression and neural networks. So this is the last part. So I hope this will bring you a flavor of regression. Okay, like regression applied. So you can see how regression optimize.cofit. Why optimize.cofit? Why not anything else? Why optimize? Because it is trying to find the regression line which is very close to your data points. How much is very close? How much is very close? It doesn't have to worry about a single point. It has to worry about all the points of your data set. Okay. And that's how you fit it. That's how you fit it. So therefore you compute the error. You compute the error of predicted and what is that error. You want to optimize that error. Okay. How you do? Optimize curve fit. Optimize curve fit. So what is so now we will see the relation between regression and neural networks. Okay, fine. All the things we learned in this. Okay. So in order to understand, we'll just give you a brief idea about neural networks, okay? And then we will use after you learn something about neural network, we will use something known as MLP for regression. That is known as multi-layer perceptron. Okay, and we will see what kind of neural network you can consider, so that you can actually get the job of regression done. Okay, that's the idea. Fine. In order to know that, you have to see some basics of neural network first. Okay. Hmm. We'll go hand in hand. So let us see. So cover some basics of machine learning a bit. So you have give a given problem to you. Okay. So usually it is like this. You have a model. Basically, you have a model. You give some input data to it. Give some input data and you will get some output based on that model. Okay. And this output is actually kind of prediction. Fine. Fine. So this is what machine learning actually does. Okay. How this is related, what it actually does, we'll see. Fine. So you'll see that this is a problem given to you. You first classify whether the problem is labeled data or not. Data, yes. It is falls under the classification of supervised learning. If it is not, it falls under the class of unsupervised learning. Okay. So if you have supervised learning, then there are two main things. That is whether it is categorical or quantity. Okay. So suppose regression. Regression deals with quantity. Regression deals with values. Regression deals with data sets, numbers. So therefore, in quantity, it falls under regression. Okay. So regression is a part of supervised learning. Okay. Suppose it is categorical. It is categorical. Categorical means classification. How one example is classification. What is classification mean? Suppose who to do like apple and good. That's the same example we'll consider in this. Okay, orange. Okay, so what happens to apple and oranges? Okay, so you have apple and oranges. So suppose you brought a truck of oranges. Okay, the shopkeeper will give you apple and oranges. What you will do with that when it comes to your home and you want to eat? You want to segregate. She wants to segregate the apple and oranges. Okay, which is apple, which is orange. So she has to classify. She will put apple into orange or apple basket, orange into orange basket. Okay, that is known as classification. Okay, that is known as classification. But you are using your brain. You are using your brain, your single brain, to do the classification. That this is orange, this is apple. How many will you buy? 2 tons. Suppose 2 tons of apple and oranges. 2 tons you have to separate. A day will pass, you won't be able to separate. Okay. So therefore, you can use the machine to separate it. Okay. You can use machine algorithms to separate it. So how machine learning can be used in classification? Automatically classify. Automatically classify. Fine. So that's the idea. So then you will see this neural network, logistic regression. I think these are covered in your other classes. Random forest and support vector machines are used. Fine. Unsupervised learning, we are not going to discuss that much because it's not falling under our case. But you can see that if it is grouped, if your data set is grouped, then you can use clustering. Okay. If I ask the whole class to go to the field and stand, do you think all will stand like this? No. Everyone has their gangs. Okay, everyone has their groups, and they arrange in their groups and talk, and that's their thing. So they arrange in clusters. Okay, so you can use this k-means. You can use this k-means and other kind of clustering algorithms here. And suppose you have a higher dimensional data set. Suppose you have higher dimensional data set. What you need to do in data analytics, you might have learned about PCA. Okay, PCA. So principal component analysis. You want to find the best features and consider those features only and discard the other features. So your problem has reduced from 7 dimensions to 3 dimensions. Okay? So that is known as dimensional reduction, like that. So yeah. So you can see like the machine learning, as the name suggests, these are the group of algorithms that try to enable the learning capability of computers. Okay, computer won't do anything by itself. Computer won't do anything by itself. You have to tell the computer, you have to make the computer learn that this is the case. Computer has to do like this, then computer will do it in a very faster way than you. Okay, so that they can learn from the data, or past experiences. The idea is that, like, suppose you can see example, like we get many skills from learning. One example I want to tell is like, maybe in your childhood times you came across cats, you came across dogs. Okay, so from a few cases, because since you are a kid, you are allowed to stay at home. Okay, now you are an adult, you can go anywhere. But as a kid, you are mostly at home, and since you are at home, many many dogs come to you. Like, not dogs, cats at least come to you. Dogs you can see from outside. Okay, so it's fine. But through that data set, you can know which is a dog, which is a cat. Okay, so therefore, when you travel to, suppose, Himalayas, suppose, just as a tour, there you see some cats and dogs. Okay, then you will know that yes, this is a cat and this is a dog. But that is not the dog you have seen, right, at your home. That is a different dog, but qualitatively the features are the same. Okay, fine. So this ability to learn from data presented to us and later can be used to generalize, to recognize new data, is one of the things we teach computers to do. And that's what exactly machine learning does. Fine. So basically, it's the simplest case. Like, you can see, you need to represent your data. Data comes in various forms. As you have learned in your first semester, data comes in various forms. What forms? Audio data, text data, numeric data, any other data sets? Fine. So you can see these are all the data representations, and you fit inside a tunable model. Okay, this is the model which takes the data and applies different optimization algorithm. Why optimization algorithm is being used? To reduce the error between the data set and the training error, like the generalized training error we learned in optimization algorithm. To reduce the training error. Okay, to reduce the training error, we need optimization algorithms. Together, you come across the trained model. That this is a trained model. Now you ask him anything, ask him to classify if this is an orange or an apple. It can classify whether this is an apple or an orange, because you have trained the model using optimization algorithms already. Through the optimization algorithm, it is already known that the prediction will have lowest loss, minimized loss. Fine. This is we come across this apple and orange case. Okay. So you can see how apple and oranges are classified together. Okay, how apple and oranges are classified together. You can actually draw a boundary. Okay, you can actually draw a boundary. So, fine. So these are all the cases, like how you know the apple is an apple, orange is an orange. How? It is bit polished. When you touch the apple, it is very polished. But when you touch the orange, it has ridges. It has ridges. And sometimes that is like, you can say texture. You can say, is it a texture? Color. You can say like it is orange and it is red. Okay. Fine. So color, you can separate them. Fine. Through shape. Maybe apples are like, decide what shape you want to give. Okay. Anything else? Smell. Okay. Orange has a very nice smell. Okay. If you eat orange in the classroom, okay, and I have a blindfolded, I can still say that someone is eating orange. But if someone eats an apple, I will not know. Okay. Has core. Okay. Apple has a core, but orange doesn't. Okay. Fine. So these are the features of the data set you have. Okay. Based on that, we want to predict whether it is an apple or an orange. Fine. Fine. So suppose this is orange, this is apple. So what you do, you want to separate these, you want to segregate these, you want to classify these apples and oranges. What does it mean to classify these into apple and oranges? That means you can segregate them. Yes, you can actually segregate them. Apple you can take in one branch, orange you can take into another branch. That way you are able to segregate them. Okay. So what does it mean by segregating? That means you can draw a boundary. You can draw a boundary between them, isn't it? I can say that this group one, this group two are segregated. Why? Because I can draw a boundary between them. Okay, fine. So this is something special. This is known as a decision boundary. It's known as a decision boundary. Okay, fine. Can there be only one decision boundary? Can there be only one decision boundary? Can this one be the decision boundary? This one can also be the decision boundary. So therefore, there can be infinitely many decision boundaries. Okay. And this is actually the case. Without the computer knowing about whether this is all, it actually does. It says that the classification problem has boiled down to a different problem. Like, what is that problem? Can you find a decision boundary for this given data set? You can find the decision boundary for that given data set. You have classified that problem. Okay. So the classification problem essentially deals with finding the decision boundary. Okay. Mark my words, mark my writing here. A decision boundary, not the decision boundary. So whenever you read anything scientific literature anywhere, be very careful regarding these two verbs, a and the. Okay, that I came to know a lot late in my career. Okay, I never used to give that much importance to a and the. A means there can be more than one, but it is the only unique one. Okay, so you can say find a decision boundary means it is saying to you that we are just finding a decision boundary out of many decisions. Already know that there can be infinitely many decision boundaries, and our job is to find any one such decision boundary. Which one is the best, we don't. Okay. However, this is a very nice example for you, but maybe in the next class I can show you that these decision boundary are not that simple. Okay, not that simple. For example, oranges are like this, oranges are like this, apples are like this. What should be your decision boundary? Yeah, your decision boundary should be a circle. I will show you using tensor playground or something with application that finding this is very hard for a neural network. I will give you this as an assignment. Okay. Last year I gave this assignment to the class. They took around 7-8 days to find what kind of neural network can actually do this classification. What kind of configuration can do this classification. Okay. Anyway, so that is the idea. Now the question comes. Now we already know that there exists infinitely many decision boundaries, and the decision boundary is not unique. Now my question is how to find the best decision boundary. How to find the best decision boundary. Which decision boundary you can take so that you will be at profit. So that whatever happens, your data will not be labeled incorrectly. Yes. So this is done by support vector machines. Okay, this is done by support vector machines. So one popular way to compute the decision boundary is SVM, support vector machine. Very intuitive algorithm based on how we make the decision. Okay, so you can see that this is our data set. Okay, I can take which one I should take. See, the red one I can take as a decision boundary. The black one also I can take as a decision boundary. Now my question to you is, which one is better, the red or the black? How many of you say red there? How many of you say black? How many of you say nothing? Not raising hand. For that, at least you should raise a hand, right? Yeah. So red or black? Why it makes you think that red? Why red? So the idea is simple. Like the idea is like this. Like suppose you took the black one. Let us take the black one. Now she found one extra apple. Okay, she found one extra apple lying while lying down. Okay, in the tree. So she got that extra apple. She want to place it. Where she will place it? On that side, on the above side of the apple. Suppose since this line is very close, and suppose you put it here, then it is wrong, right? Then it is wrong. Yes, but it is wrong for the black decision boundary, but it is still correct for the red decision boundary. Are you getting the logic? Your black decision boundary has failed to classify the apple case because the black decision boundary is this side, orange has fallen. Okay, but if you see the red decision boundary, on the left of the red decision boundary, blue balls are still there. That is apples. So even if you add something to your data set, your red decision boundary is fine. Red decision boundary serves the purpose, but black decision boundary failed to serve the purpose if you add an extra apple. Okay, that is a very intuitive way to think this problem, that why red one is better, why red one is better. Okay, and why not black one. Now to think of mathematically, how to, like, logically, I would say, how to logically think that this red is the case and not the black one. Okay, so this is exactly what I wanted to tell. If you add a new data point like apple, you can see the black point might not be able to detect it. Okay, of course you can add something here and still it works, but that is not my point. My point is it should not fail at any one case. That is my aim, but it fails in this case. Above, below the red line, here, 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 here I put the blue. Okay, then what happened? Yeah. So here what happens? Hmm. Yes. So yeah, that's also a correct point. What you see from this, see what you saw when you keep here, it black fails. Okay, black fails. Black fails. When you keep here, black wins. Okay, why? Can you observe that if the point is close to the decision boundary, it fails. The blue point is close to the black line, very close, almost intersecting. So it fails. But the moment your point is a distant from the black line, it wins. So your job should be like this. Your job should be as much as remain, the decision boundary should remain as much far possible from your data set. Okay. That's the takeaway message. I accept red passes, red fails. But it teaches only one thing, that if in classification, your data points should be as much away as from the decision boundary as possible from either of the parties. Okay. Now the idea is how to generalize this concept. We can generalize this concept using something known as buffer. Using something known as a buffer. Okay. What is a buffer? So suppose take this example. Take this example A and B. We took the red curve red decision boundary, okay, separating or classifying the two data sets. Now the idea is simple. It has a wider buffer. Part A has wider buffer. I hope you can see it. The wider buffer means this width, yellow line. It has a wider buffer. But part B is not an ideal candidate for the decision boundary. Why? Why? Because the buffer is low. The buffer is less. Since the buffer is less, its job as a decision boundary has failed. Okay. So if you want to have a good decision boundary, the buffer should be more. Okay, the buffer should be more. So this is a narrow buffer, this is a wide buffer. So select the decision boundary. Out of all the available decision boundaries, select a decision boundary which has a wider buffer, not a narrower buffer. Agree? Okay. Fine. So this is the design of that SVM algorithm, which we will not go into detail, but this is the basic of SVM algorithm. Okay, how SVM can be used to find the best decision boundary. It will search the decision boundary which has a wider buffer. Okay. So it first forms a buffer for the boundary line to the points in classes that are close to the line. And these are known as support vectors. These are known as support vectors, and hence this is known as support vector machine. Okay. The idea is simple. These are vectors. These are vectors, but these are something more than vectors. That these are support vectors. These are support vectors. Why these are known as support vectors? Because they support this decision boundary line. They support this decision boundary line, and therefore these are known as support vectors, and hence the name of the algorithm support vector machines. Yes, so the classification problem can be boiled or questioned in a different way. What is the question? The problem has boiled down to this. Given a set of support vectors, can you find which line has the maximum buffer? Okay, given all the support vectors, all the possible support vectors, which curve gives you the maximum buffer? Okay, that's the idea. Okay, fine. And that line which has the maximum buffer can be chosen as the decision boundary. Fine. So the that's the idea of classification. We spent some time. I hope this gives you an idea. Okay. The most popular package we have dealt so far is something known as scikit-learn for machine learning algorithms. But for deep learning, we have been using TensorFlow and PyTorch, so on. Okay. I think we have the first part of the course where we were learning optimization and deep learning, the interchange of them. We are mostly using TensorFlow and PyTorch. But now you will see that in the classification algorithm in your courses, you will use scikit-learn. Okay. There is a very famous data set known as iris data set. It has the flower iris, and the flower iris has many different patterns. And how scikit-learn you can use to classify all the flowers. That this is that flower, this is this flower, this is that flower. How to classify? Okay, fine. So the idea is, let us come to regression. So we have so far covered least square regression. Okay, for simple cases, of course, and we have an analytic form that we can fit the data. Y cap equals to W0 plus W1x. You have formulas for W0 and W1, how to compute them. Okay, and we compute it. Okay, but machine learning approach are more flexible in the sense that you can fit any function of data without knowing the underlying analytical form at all. Okay, so you just give the data set, and machine learning algorithms can actually predict what is the value, how it can fit the data. That's the idea. Okay, you can use these things, random forest, artificial neural network, support vector machine, so on, to do or perform regression. That I think you will learn in your deep learning or deep learning class. More about this random forest, feed forward neural network, RNN, all these things. How to compute regression using that. Okay, so that's the idea. So yeah. Maybe after the break, we can learn into artificial neural network. We learn a part of it, artificial neural network, to perform regression. Idea is ANN to perform regression. That should be the next part of the lecture. We'll meet at 11.